Okay, next in this video we're going to start section 5.5, which is about a specific type of transformation called an inversion. Now this is not an isometry and it's not a homothety or a dilation or a similarity transformation. Okay? An inversion is a different type of transformation that we're going to need when we eventually look at the Poincaré model of hyperbolic geometry. We're going to need a way to create orthogonal circles, as we're going to see what this winds up doing at some point. Okay? So let's start by looking at the definition. Okay? It says let O be the center of a fixed circle of radius r in the Euclidean plane. So an inversion starts with a fixed circle with a given center and radius. Furthermore, let P be any point in the plane other than O. An inversion of the circle, which we'll denote with an I, sub O comma r, centered at O, radius of r, is a function such that IO of r of P, IO r of P equals P prime. So the inversion sends P to P prime, where P prime is on the ray OP, and it sends it to a distance. This is kind of like a dilation, but a little bit different. It sends it to a distance to where OP times OP prime is equal to r squared, the radius of the circle squared. So P prime will be called the inverse of P, so they're inverses of each other. Now the center of inversion, O is called the center of inversion, and r is the radius, r squared is called the power. Now we have to have somewhere to send the center as well if we want everything to have an image under an inversion. So basically the center is going to go to infinity, so we're going to have to add a point to the plane representing infinity, which we represent with a capital omega. Looks like the little horseshoe or something there, the capital omega. So the Euclidean plane with one ideal point, infinity, basically appended to it, we call the inversion plane. So let's take a look in GeoGebra and see what inversion is all about. Okay, so I have a circle here. The center of my circle is called A. It's just a label for the center, and the distance from A to B would be the radius of the circle. If you square that, you get 6.15 for this specific circle. So r squared is 6.15. Here's a point C. I've computed the distance from A to C, which is 1.71, of course rounded off. And then from A to C prime is 3.59. And AC times AC prime equals 6.15. So if this is C, there's the point that lies on the ray. Let me put the ray in. Okay. So the inverse of C is going to lie somewhere on this ray, A to C, and it lies at a distance so that this is true, so that AC times AC prime is equal to the radius squared. Okay. We're going to look at some ways to construct this. We'll look at a couple of theorems. If the radius, or if the point is actually on the circle, then C and C prime are the same thing, because the distance AC is going to be the radius, and then r squared will give us r squared. Otherwise, if the point's inside the circle, the inversion has to be outside. Since AC is less than r, AC prime has to be bigger than r. And then the opposite of that's true as well. If AC is bigger than r, AC prime has to be less than r in order for AC times C prime to be r squared. Okay. So we'll see what this does to circles and angles and things like that, but that's basically what an inversion is. So the theorems there, which are just what I said, well, the inversion is a transformation of the inversion plane. It is a one-to-one and onto function from the plane to the plane. The center of the circle goes to infinity, and infinity goes to the center of the circle. All other points do what we've defined for an inversion. Points on the circle are fixed, because AC times AC is going to be r squared, so C prime equals C. And then, as I just pointed out, if the point's on the interior of the circle, then AC is less than the radius, so AC prime is going to have to be bigger. The point's going to have to be outside the circle, and then the converse. If C is outside the circle, AC is bigger, so AC prime has to be smaller and has to be inside the circle.